Hello, and welcome to part 3 of our discussion of transmission lines. In parts 1 and 2, we showed that when you apply a signal to a transmission line with a mismatched termination, you will get reflections and set up standing waves on the line. This will clearly affect the voltage and the current as a function of distance from the load. As a direct result, it will affect the apparent impedance viewed at some distance from the load. Ultimately, we are interested in the apparent input impedance as viewed by the signal source, where the distance from the load is the length of the cable L. This will be the focus of our discussion in this concluding session. Recall that in part 2, we derived this pair of expressions for V0 plus and V0 minus, the amplitudes of the potential of our transmitted and reflected waves on our transmission line. We substituted these expressions into our equation for V of z. Recall that I0 plus equals V0 plus over Z0, and we substituted our expression for V0 plus. And recall that I0 minus equals V0 minus over Z0, and we substituted our expression for V0 minus. We substituted these expressions into our equation for I of z. The terms L and Z combined to put L minus Z into all of our exponential terms. This term L minus Z is the distance from the load, which we called Z prime. This is precisely what we are interested in because we are ultimately looking to characterize the apparent impedance of our transmission line as a function of distance from the load. For this reason, we made a variable substitution of Z prime for L minus Z to give us this pair of equations for V of z prime and I of z prime. I said we would come back to these, and now here we are. We'll rearrange the exponential terms and group them with their like coefficients of ZL and Z0, and was this? We have these sums of e to the gamma z prime and e to the minus gamma z prime terms. These look a lot like the hyperbolic trig functions we discussed in the math session. Remember your curmudgeonly uncles who I said you should invite over for dinner once in a while? Well, here they are, and they're looking for where you keep your beer. We can rewrite V of z prime and I of z prime in terms of hyperbolic cosine and sine functions, and we'll take the ratio of them, which gives the impedance at a distance z prime from the load. This is precisely what we are looking for, and we're almost there. We divide numerator and denominator by the hyperbolic cosine of gamma z prime, then we set z prime equal to L to get this expression for the input impedance of a lossy transmission line. This equation may look a bit scary, but stick with me just a bit longer. This is the full equation for a lossy transmission line where gamma is a complex number. For the lossless transmission line simplification, the real part alpha equals 0, leaving only the imaginary component, j beta. Recalling the identities of the standard trig functions and our discussion of hyperbolic trig functions in the math session, hyperbolic cosine of a purely imaginary argument reduces to the standard cosine function. Hyperbolic sine of a purely imaginary argument reduces to j times the standard sine function, and hyperbolic tangent reduces to j times the standard tangent function. So, we can substitute j tangent of beta z prime for the hyperbolic tangent terms, and set z prime equal to L to get that the input impedance of a lossless transmission line is given by Z0 times ZL plus J Z0 tangent of beta L over Z0 plus J ZL times tangent of beta L. This equation may also look rather scary, but it is worth pointing out that it is the basis of the Smith chart, and it provides a tremendous amount of information when you apply some bounding cases, which we are going to do right now. First, we'll recall that beta is defined as 2 pi over the wavelength lambda, and it also equals omega times the square root of LC. Both of these substitutions will come in handy. When ZL equals Z naught to provide a matched load, we substitute Z naught for ZL, the numerator and denominator are equal and cancel each other out, so Zin equals Z naught. And that's great. For a matched load, the input impedance simply looks like Z naught. For a shorted termination where ZL equals 0, the ZL terms go away and the Z naught terms cancel, so that the short circuit impedance ZSC equals J Z naught times the tangent of beta L. When the argument x of the tangent function, expressed in radians, is very small, then the tangent of x approximately equals x. Thus, for an electrically short cable, meaning that it is much shorter than a wavelength, we can say that the short circuit impedance is approximately equal to Jz naught beta L. We can make substitutions for Z naught and beta, I told you it would come in handy, to get that the short circuit impedance equals the inductive reactance. Note that capital L is the inductance per unit length, and multiplying it by lowercase l gives the total inductive reactance. For an open termination where ZL is infinite, the ZL terms dominate, the Z naught terms effectively go to 0, and the ZL terms cancel so that the open circuit impedance ZOC equals Z naught over J tangent of beta L. Again, for an electrically short cable, we can substitute beta L for tangent of beta L, make our substitutions for Z naught and beta to get that the open circuit impedance equals the total capacitive reactance. Looking at these two expressions for short circuit and open circuit impedance, we see that if we take their geometric mean, we get Z naught. This means that the characteristic impedance of a cable can be obtained from measurements of the short circuit and open circuit impedances. These can be easily measured directly, as I will show you shortly. Also, when we look at the electrically short expressions, when we take their geometric mean, we get the square root of L over C. So, the pieces all fit together, as they must. Now let's look at what happens when the cable is electrically long, that is, when it is a significant fraction of a wavelength. When L is a half wavelength, our tangent argument beta L equals pi. Tangent of pi equals 0, so the tangent terms go away, and the Z naught terms cancel, so that the input impedance equals the physical load impedance ZL. And this is also true when L equals multiples of lambda over 2. When L is a quarter wavelength, our tangent argument beta L equals pi over 2. Tangent of pi over 2 is infinite, so the tangent terms dominate, the non-tangent terms effectively go to 0, then the J and the tangent terms cancel, so that Zn equals Z naught squared over ZL. The significant thing to note here is that Zn is inversely proportional to the physical load impedance ZL. This means that when the load is a physical short circuit, it will look like an open circuit a quarter wavelength away. And when the load is a physical open circuit, it will look like a short circuit a quarter wavelength away. And this is also true for L equal to odd multiples of lambda over 4. If you remember nothing else from this session, I beg of you to remember this. Let's look at a couple of examples. Let's say you have some device that you want to connect to what we'll call ground. So you hook up a ground wire, run it over structure, and for whatever reason, you connect it to a point on the structure a meter away. Whether you like it or not, this configuration will behave as a wire above ground transmission line. At 50 megahertz, the 1 meter wire will be a quarter wavelength long, and your device will see an open circuit a quarter wavelength away from the connection point. Thus, your grounding connection is doing you absolutely no good at that frequency. Now, let's say you have a pair of conductors from separate circuits running in parallel, again over a 1 meter distance, and you want them to be isolated. Again, whether you like it or not, this configuration will behave as a parallel wire transmission line. At 50 megahertz, it will be a quarter wavelength long, And your signal source will see a short circuit a quarter wavelength away from your alleged isolation, and you will almost certainly get some coupling between these two circuits. So, at these quarter wavelength resonances, the impedances are not what you think they are, and your circuits will not behave the way you think they should. But being aware of the physics can help you quickly diagnose and address any of these behaviors when you come across them. And that's when and not if.
Things are seldom what they seem. Skim milk masquerades as cream. High-lows pass as patent leathers. Jackdaws strut in peacock's feathers.
Very true, so they do.
We'll look at one last example when L is an eighth of a wavelength. Here, our tangent argument beta L equals pi over 4. Tangent of pi over 4 equals 1, and when we look only at the magnitude, we see that the magnitude of Zin equals Z naught, independent of the load impedance. And this is true for L equal to odd multiples of lambda over 8. This can explain why you might see some interesting behavior at these frequencies. Because your signal source will see only the characteristic impedance of the line, no matter what the physical termination is. Let's look at an example of a 1 meter length of a 50 ohm transmission line. Assuming a typical dielectric of Teflon or equivalent, we can estimate the wavelength in meters to be approximately 200 divided by the frequency in megahertz. Thus, we can expect our resonances for a half wavelength to occur at about 100 megahertz and multiples, for a quarter wavelength at about 50 megahertz and odd multiples, and for an eighth of a wavelength at about 25 megahertz and odd multiples. Here is a graph of the input impedance of the 1 meter cable for a shorted termination. The inductive reactance dominates at low frequencies. We see nulls for a low impedance at multiples of 100 megahertz, and we see peaks for a high impedance at odd multiples of 50 megahertz, all as expected from the previous discussion. Here is a graph of the input impedance of the 1 meter cable for an open termination. The capacitive reactance dominates at low frequencies. We see peaks for a high impedance at multiples of 100 megahertz, and we see nulls for a low impedance at odd multiples of 50 megahertz. Again, all as expected from the preceding discussion. Here is a graph showing the curves for both the short and open terminations, along with the impedance for a matched termination, which is a straight line at 50 ohms. The curves cross at odd multiples of 25 megahertz at a value of 50 ohms, again as expected from the preceding discussion. As I said earlier, this equation provides a tremendous amount of information once you know how to extract it. So, that's what the theory says. Now let's see how things look in real life. This is another simple setup that I encourage you to try in your own lab, consisting of a network analyzer configured for an impedance measurement, an RG58CU coaxial cable of approximately 1 meter length, and various terminations, 50 ohms, short, and open. Here is an example datasheet for RG58CU cable. The parameters of interest for this discussion are highlighted here. It provides the characteristic impedance and the capacitance per unit length, but not the inductance per unit length. Well, knowing that the characteristic impedance equals the square root of L over C, we can back out an estimated value for the inductance per unit length of about 250 nanohenries per meter. It does not provide the dielectric constant, but it provides what it calls relative signal propagation. This is the speed of propagation as a fraction of the speed of light, u over c, given as 66.3%. From this, we can back out a dielectric constant of about 2.3, which is right in the typical range. Given this value for u over c, we can use our estimate for the wavelength in meters to be approximately 200 divided by the frequency in megahertz. Just as with our theoretical model, we can expect our resonances for a half wavelength to occur at about 100 MHz in multiples, for a quarter wavelength at about 50 MHz in odd multiples, and for an eighth of a wavelength at about 25 MHz in odd multiples. Let's start with the 50 ohm termination. On all of the following plots, the frequency axis will be on a logarithmic scale, running from 1 MHz to 1 GHz, and the magnitude of the measured impedance will be on the vertical axis, also on a logarithmic scale. The measured impedance at the network analyzer is a nice flat level of 50 ohms up to about 200 MHz, as we expect. There are some variations above 200 MHz due to imperfections in the setup. For one thing, BNC connectors are less effective at these frequencies, but this is sufficient for the present discussion. Now let's look at a shorted termination. We can clearly see the same general shape as our theoretical prediction. At low frequencies, where the cable is electrically short, the inductance dominates. In this linear part of the curve, we know that the measured reactance equals j omega times capital L for inductance per unit length, times lowercase l for length to give us the total inductance. We're only interested in magnitude, and we substitute 2 pi f for omega. We could pick any point on this linear part of the curve for this calculation, but if we pick 1.59 megahertz, the math gets much easier, because 1.59 times 2 pi is approximately 10. That gives us 10 times 10 to the 6th radians per second, and that means that if we divide the measured reactance by 10, we get the total inductance in microhenries. Our measured reactance at 1.59 megahertz is about 2.62 ohms, which gives a total inductance of 262 nanohenries. For our 1 meter cable, that gives 262 nanohenries per meter. This is within 5% of our predicted value of 250 nanohenries per meter, which provides good agreement. We get our first null for a half wavelength resonance, where the short circuit looks like a low impedance of a little over an ohm, at just under 97 megahertz, which is within 4% of our predicted frequency of 100 megahertz, also good agreement. This is also true at multiples of that frequency. We get our first peak for a quarter wavelength resonance, where the short circuit termination looks like a high impedance of about 3 kiloohms, high compared to 50 ohms, at 48 megahertz. This is also within 4% of the predicted frequency of 50 megahertz, and it is also true at odd multiples of that frequency. Now let's look at an open termination. Again, we can clearly see the same general shape as our theoretical prediction. At low frequencies where the cable is electrically short, the capacitance dominates. In this linear part of the curve, we know that the measured reactance equals 1 over j omega CL, where C is the capacitance per unit length, and CL is the total capacitance. Again, we're only interested in magnitude, and we substitute 2 pi f for omega. As we did for our inductance calculation, we will measure the reactance at 1.59 megahertz. When we take the reciprocal and divide it by 10, we get the total capacitance in microfarads. Our measured reactance at 1.59 megahertz is just under a kiloohm at 996 ohms, which gives a total capacitance of 100.4 picofarads. For our 1 meter cable, that gives 100.4 picofarads per meter. The datasheet specified 100.7 picofarads per meter. That's agreement to within 0.3%, and you don't get much better than that. We get our first peak for a half wavelength resonance, where the open circuit looks like a high impedance of about 1.5 kiloohm, again high compared to 50 ohms, at 98 megahertz. This is within 2% of our predicted frequency of 100 megahertz, so excellent agreement. And this is also true at multiples of that frequency. We get our first null for a quarter wavelength resonance, where the open circuit looks like a low impedance of just below an ohm, at about 49 MHz, which is also within 2% of the predicted frequency of 50 MHz. This is also true at odd multiples of that frequency. Now we'll look at both the open and short circuit impedances on the same plot. Recall that at any frequency, the geometric mean of these two impedances should equal the characteristic impedance Z0. Instead of doing any calculations, we can simply look at where the curves meet, which is indeed at a value of darned close to 50 ohms. This occurs at about 24 MHz, which is within 4% of the predicted frequency of 25 MHz. And this is also true at odd multiples of this frequency. Once again, theory and experiment are always two sides of the same coin. And as we have just seen, the theoretical transmission line model provides excellent agreement with measured results, and we can have a high degree of confidence when using it to analyze real-world problems. To summarize and repeat for emphasis, interconnections matter. For interconnections that are longer than 1/10 of a wavelength, they must be treated as transmission lines. You need to use a controlled characteristic impedance, Z0, and you must terminate them in a matched impedance. The velocity of propagation in an air dielectric is the same as the speed of light in free space, which is 3 × 10⁸ meters per second, or about a foot per nanosecond. And the wavelength is equal to 300 divided by the frequency in megahertz. Rules of thumb for most non-air dielectrics: the speed of propagation is approximately 2/3 of the speed of light, and the wavelength is approximately equal to 200 divided by the frequency in megahertz. Mismatched terminations can cause reflections and distortions in the desired signal. They can compromise system operation, and in digital systems, they can completely freeze up your state machine. And they can look like very different impedances at some frequencies, particularly when the length is an odd multiple of a quarter wavelength, producing uncontrolled and undesired effects, such as currents flowing in undesired places. Knowledge of these principles will help you to prevent problems and to recognize and diagnose such problems when you see them. This will wrap up our discussion on transmission lines, at least for now. These videos are not intended to replace any serious course of study at the university level, but I hope I have at least provided you some anchor points that you will find helpful in your own continued studies, and especially in your daily work. Ciao for now.
I like to dream, yes, right between the sound machine. On the cloud of sound, I drift in the night. Any place it goes is right. Goes far, flies near, to the stars away from here. Well, you don't know what we can find. Why don't you come with me, little girl, on a magic carpet ride? You don't know what we can see. Why don't you tell your dreams to me? Fantasy will set you free. Close your eyes, girl. Look inside, girl. Let the sound take you away.